any type of binomial, so x plus y to the 1, to the 2, to the 3, to the power of 10 in a quick and easy way. Solve problems involving the binomial theorem. So we're going to start by introducing the Pascal's triangle, which is a triangular array of numbers in which those at the ends of the rows are always 1, and each of the others is the sum of numbers in the row above it. So if I were to start the Pascal's triangle, I would start with the value of 1, so this would represent 1. In row 2, we're going to continue that pattern. The outside values would be 1. In row 3, you'll start to notice a patterning happening. So the outside values are still 1, but as we get our middle value here, we add the previous 2 terms to get this middle value. So 1 plus 1 gives me 2. In row 4, I'm adding these to get 3. Same thing here, 1 plus 2 to get 3. Row 5, again, I'm adding each of these terms to get these middle values. 4, 6, 4, and 1. So you can continue this Pascal's triangle to an infinite number of rows. 5, 10, 10, 5, and 1. Row 7. Right, so if we wanted to number 8, our 8th row would be 1, 7, 21, 35, 35, 7, and 1. And then you can continue that over and over. So what does Pascal's triangle use for? So one thing Pascal's triangle can be used for is what we call pathway problems. So I have 3 examples of pathway problems, starting with a very simple one. Use Pascal's triangle to solve the pathway problem. How many pathways are there from A to B allowed to backtrack? So I need to get from point A to point B. So think of this as like street blocks. This is going west, this is going south, and so we can't backtrack. So we can never go north or east. We always have to get closer and closer to B. So if we think of the number of ways we could get there, well, if I could go, in order to get to this next intersection from A, there's only one possible way to get to this intersection. Similarly, there's only one possible way to get to this intersection. Right? The only way to get there is to walk straight west. Or straight east, sorry. Would be 1. Or to get to this intersection down here, the only way I could get here would be to go straight south. So one way. Same thing, to get to this intersection, there's only one way to get there, is by going straight south. So even though I'm through this intersection, we're talking about the number of ways we can get to each intersection. So then if we were to talk about this intersection here, I could go east and then south. That would be one way to get there. Or I could go south and then east. That would be a second way. So to get to this point here would be 2 possible ways to get there. What about this location? I could go all the way east and then south, so that would be 1. I could go just east to the first intersection, go south and then east again, so that would be 2. Or I could go south and then all the way east, so that ways. Okay. Same thing to get to this intersection. I could go straight south and then east, that's 1. I could go south, east, and then south again, that's 2. Or I could go east and then straight south, so that would be 3. So what you should see unfold is these numbers at these intersections relate to our Pascal's triangle. 1 plus 1 would give me 2, give me 3. 1 plus 2 would give me 3 here. To get to this intersection here, let's count them. I could go all the way east and down, that's 1. I could go east to the second intersection, go south and over, that's 2. East and then all the way over, that's 3. Or I could go way over, so that's 4. So 3 plus 1 give me 4. So in order to get from A to B, I'm simply using the Pascal's triangle to move my way over to B. So to get to this intersection is going to be the sum of these 2 intersections, which would be 6. 6 plus 4 would give me 10. So how many pathways are possible to get from A to B? would be 10 possible pathways. Now the other way you could do this than using your Pascal's triangle is using factorial notation. You could take the total number of intersection points, east and south, 1, 2, 3, 4, 5. So south gives me a total of 5. So if I take 5 factorial and divide it by my identical directions, so I have 3 intersections east and 2 intersections south, this will always also give me my same answer. So whether you use Pascal's triangle or factorial notation, you've got this answer. But as pathways get more complex, sometimes this can't be used and you have to use the Pascal's triangle, such as the next example. Okay, so if I again want to get from A to B, going through this set of pathways, well, again, going straight east, and I can't backtrack, so I always have to go east and south. So all of these would be one way to get to here, one way to get to here, and then now I'm going to start my Pascal's triangle. So 1 and 1 would give me 2, 2 and 1 would give me 3, 1 and 2 would give me 3 here. So to get to this location here would take me 6. If I continue down here, this would 4 ways, 5 ways, 6 ways to get to this location. If I continue on, 4 plus 6 is 10. This would be 15. This would be 21. So now I need to get to this location. So in order to go to this next location, I have no other number to add to this 6, so this value isn't going to change. Okay? Because there's 6 ways to get to here, but to get to this next location, the only way I can get there is from this intersection, which is the 6. So this number of ways isn't going to change. This is still going to be 6 to get here. It's still going to be 6 to get to here. And it's still going to be 6 ways to get to there. And I need to add, so to get to here I can either come from the 10 or the 6, so that would be 16. To get to here from the 6 or the 16 would be 22. This would be 28. 16 and 15 is 31. This would be 52. This would be 63. Sorry, 53. 53 and 28 ends up to be 81. 53 and 52 and 53 would be 105. Okay, and so to get to this location here, the only way I can get there is from the 52, and there's no other value to add, so this has to be 52. Same with this location, has to be a 52. Okay, so now I'm going to add again, so this would be 157, 105 and 81 gives me 186, 186 and 157 gives me 343, 157 and 52 gives me 209, and then finally 209 plus 343 gives me a total of 552 ways, so different pathways I can get to B. Alright, another type of pathway problem you'll come across is like a pinball machine, right? So it's like we're dropping a ball here. These are all the pins that the ball's going around. Okay, so in order to get to either side of this pin would be one possible way. One way to get here, one way to get here. Or if the ball continues to drop, there's only one way here, one way to get here, one. So there, to get into this slot at the bottom here, there's only one possible. Same thing to this slot way over here. There's only one possible way the ball can drop. So that's why the majority of the balls are going to fall mostly in the middle, because once we start to add these values, the ball can go here or here. So there would be 2 ways to get to this position. And then to get to this position, there would be 3 ways. So again, I'm using Pascal's triangle here. There would be 3 ways to get to here. there would be 4 ways to get to this position, 6 ways to get to this position, or 4 to get to this slot. Okay, so that's why the majority of the balls would end up in this middle position, because this would have the most number of pathways. And you could take this and move on and talk about probabilities and stuff like that, but we don't do probabilities in Math 30. All right, so our Pascal's triangle actually relates to combinations. And so a quick and easy way to relate these values in the Pascal's triangle, rather than writing the entire triangle out, is to simply relate them to combinations. So if you notice, we're talking about row 7. So this very first row, we'd start at 0. So row 1 relates to combination where n is going to start at 0. Okay, so 0 combination 0, well, this just will always equate to 1. Okay, it's like a special value. 1 combination 0, and then my second row I'm going to start with n equals 1. 1 combination 0, if I evaluate that, would be 1. 1 combination 1 would be 1. 2 combination 0, so any combination I've taken and I take times is going to occur once. So this is just an assumption of a number. It doesn't really make sense in terms of a combination, but we use it in order to create this Pascal's triangle. 2 combination 1 would relate to 2. 2 combination 2 equates to 1. And we can continue on. So 3 combination 0 is 1. 3 combination 1 is 3. 3 combination 2, combination 3 is 1. So as you can see, as our rows get bigger, our n value always starts at n, and our r value starts at 0 and works its way up to our n value. That our n value is always 1 less than the row number we're working in. Okay, so if we're working with row 7, our n value should be 6. If we're looking for row 9, our n value should be 8. Okay, and so on. So n is always in our combination is always 1 less than the row number. Pascal's triangle. All right. So how does this help us? Well, it helps us to actually expand binomials. So we haven't really gone much further to expanding an x plus y to the power of 3, possibly an x plus 4 to the power, x plus y to the power of 4. So let's say I expanded this. X plus y to the power of 0. Well, anything 0 is just going to give me 1. If I expanded x plus y to the power of x to the power of 1, this is just going to be x plus y. If I expanded x plus y to the power of 2, I would get an x plus 2xy plus y squared. Expanded an x plus y to the power of 3, recognize what this means is I'm taking an x plus y times an x plus y times an x plus y. So technically I'm taking an x plus y squared. Well, x plus y squared we've just expanded, so I'm going to take an x plus y now and multiply it by an x plus 2xy plus y squared. Now if I expanded this through, I'd have to run my x through my set of brackets, so we get an x squared plus 2x squared y plus xy squared. Oh, sorry, this should be an x cubed. There we go. And then we're going to run our y through, so we get an x squared y plus 2xy squared plus a y cubed. So if I were to collect like terms here, my expansion becomes x cubed plus 3x squared y plus 3xy squared plus y cubed. And then if we expanded an x plus y all to the fourth, well, really what this means is an x plus y squared times an x plus y squared. The expansion of each of these we did above is an x plus 2xy plus y squared times an x squared plus 2xy plus y squared. This should have been squared up here. All right, so expanded this through, I now have to run my x squared through each value. So I get an x to the fourth plus 2x cubed plus x squared y squared. Now I'm going to run my 2xy through plus 2x cubed y plus 4x squared y squared plus 2xy cubed. Now I'm going to run my y squared through. So plus x squared y squared plus 2xy cubed plus y to the power of 4. So I have an x to the fourth. My x cubed y, x cubed y, I have 4 of them. I have how many x squared y squareds? I have 1, 4 here and 1 here, so I have 6 x squared y squared. And then I have 4, so these are gone. It's easier if you start canceling. And then I have 4 of these, x, y cubes, and then I have 1 of these. All right, so the whole idea of this is to be able to expand something like x plus y to the power of 9, but I don't want to expand this using this form. It's very slow, it'll take me forever, plus it's easy to make mistakes. So there is a expand any binomial to any power, okay, whether that power is 9, 100, infinity, doesn't matter. There is a way to figure this out. So what we want to recognize is, first of all, we're going to highlight our coefficients here. So if we start to highlight the coefficients, at 0 this is 1. The coefficients of this would be a 1 and 1. Coefficients here is a 1, 2, 1. Coefficients of this is a 1, 3, 3. Here we have a 1, 4, 6, 4, 1. So what the coefficients start to do of each of these expansions, it's actually creating the Pascal's triangle. So row 1 of the Pascal's triangle relates to the coefficient of x plus y to the power of 0. The coefficients of x plus y to the power of 1 relates to row 2. The coefficients of row 3 relates to x plus y to the power of 2. This relates to row 4 on our Pascal's triangle. And this relates to row 5. Okay? And so if I, let's say, wanted, let's go way down here, an x plus y to the power of 5. Well, the power of 5, the coefficients would end up to be my 6th row of my Pascal's triangle. So my coefficients would be a 1. And then the other is the exponents on x start at this power of whatever it is and decrease by 1 each time. So it starts at 4, and then my next term is 3, my next term is 2, my next term is 1, my last term is 0. And then my exponents on y do the opposite. They start at 0 and increase by 1 each time. So this is y to the 0, y to the 1, y squared, y cubed, y to the 4. So if I wanted to expand this using the coefficients of my Pascal's triangle, this would be 1x to the power of 5 plus my next coefficient of my Pascal's triangle would be 5, x to the 4th y, so now my y's are going to increase, my x exponents are going to decrease, plus 10 is my next coefficient, x cubed y squared plus 10x squared y cubed plus 5 plus finally y to the power of 5. So a way quicker way to expand this binomial obviously is to use our Pascal's triangle and this patterning that happens between our exponents of x and y. So when we talk about properties of the expansion of power of n, there are how many terms in each expansion. So if you notice, n value is, if n was 4, we had 1, 2, 3, 4, 5 terms. When n was 5, we had 1, 2, 3, 4, 5, 6 terms. So there are always one more terms than our n value in our expansion. The sum of the exponents of x and y in each term should always equate to your n value. So if we were to look at the exponents, this is a 5. The next term, 4 plus 1 would equate to 3 plus 2 should equate to 5. 2 and 3 should equate to 5. So the sum of the exponents of x and y will always add up to our n value. The exponents of x decrease by one term by term from n to 0. So my are decreasing by 1. My exponent to increase by 1 from 0 to n. Coefficients in each expansion are created from the Pascal's triangle. The row number will always be n plus 1. So if n is 4, my row number in my Pascal's triangle would be 5. And if n is 5, then we're talking about row 6, and so on. The sum of the coefficients in the expansion is, so if I were to add the coefficients in any expansion, we're going to talk about the sum now. So if I took the sum of this first of this triangle, the sum of that would be 1. The second row would be 2. The sum of the third row would be 4. The sum of the fourth row is 6, 8. The next row would be 16. The next row would be 32. So you can start to see a patterning happening. 1, 2, 4, 8, 16, 32, 64, 128, and so on. So the sum of the coefficients in the expansion is going to be 2 power n. So 2 to the 0 gives me 1. 2 to the 1 gives me 2. 2 to the 2, 4. 2 to the 3 gives me 8. 2 to the 4, 16. 2 to the power of 5 gives me 32. So if I wanted to find the sum of the coefficients in any expansion, if I take 2 to the power of n, whatever your exponent of n is, sum of the coefficients in that row. All right, so moving on, this moves us on to what we call using the binomial theorem. You can use the binomial theorem to any power of a binomial expansion. So remembering when our Pascal's triangle actually relates to our combinations, so rather than having to write out the entire Pascal's triangle, these values are directly related to our combination values. So that means these coefficients in our expansion related to our combination values. So for example, if I wanted to expand any binomial, x plus y to the power of n, this first coefficient is going to be n combination 0. X to the power, y to the power